Good morning, my dear students. I would like to welcome you back for our online live and recorded classes for physics. Okay, we will be today dealing with the topic mutual induction, and just a reminder to you that we are doing the 4th unit, which is named as electromagnetic induction and alternating currents. All right. Now you know electromagnetic induction is like the opposite of your electromagnetism. Like if you have any change in magnetic field linked with a coil, there will be an EMF or a current set up in the coil, and that is known as electromagnetic induction, and the current induced is called induced current, and the EMF so induced is called induced EMF. Okay. And again just a brief revision, there is a law which will be giving you the direction of the induced current. The direction of the induced current will be in such a way that it is going to oppose any change in the magnetic field that is actually creating the current. That means it does not like whatever is producing the current, so it will just try to oppose the cause. Alright. And in today's class, as I told you, we will be dealing with mutual induction. Before we proceed to mutual induction, let me give you a brief revision of self-induction, which we have already done in our previous classes. Self-induction is nothing but you have a coil, okay, and if there is any change in magnetic flux linked with this coil, suppose I increase or decrease the current, okay. If I increase or decrease the current in a coil, there will be a change in magnetic flux linked with the same coil, due to which an EMF will be induced. So, due to one current, another current will be induced in the same coil. This is called self-induction, okay, and it occurs in one coil. So, cause and effect are in the same coil in self-induction, okay, and we had also done the coefficient of self-induction or self-inductance denoted by the letter L, okay, and you know that if there is a current flowing, there will be a magnetic flux created in the coil, which is directly proportional to the current flowing. Removing the sign of proportionality, you will get L I, and this is called self-inductance or coefficient of self-induction, okay. And from Faraday's law, we had phi is equal to minus di by dt, okay. Sorry. From Faraday's law, we had the induced EMF, okay, induced EMF was equal to minus di by dt, okay, that is the not I, d phi by dt, that means induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. That is what Faraday's law states, and from here you can easily find out the expression for L. E is equal to minus d by dt, and our phi is Li. So, if I just simplify this, E will be equal to L minus L di by dt, okay. Now, if my di by dt happens to be equal to 1, that means the rate of change of current linked with the coil is equal to 1, then E will be equal to minus L. That means self-inductance is, or coefficient of self-induction is equal to the induced EMF induced in a coil, where the rate of change of current linked with the coil is equal to unity, okay. Similarly, we are now going to proceed with mutual induction, okay. Mutual means here you are not dealing with one coil, you are dealing with two coils. So, that means there should be a pair of coil. You have coil number 1, okay, this is called primary, where you are actually sending the current. Of course, you should have a key to increase or decrease the current, and this induction does not occur if the current is steady, the current has to be variable. That means, how do you make the current variable? Initially the switch is off, current is 0, put the switch on, the current gradually increases. So that means we are changing the value of current. Or initially if the key is off, okay, the key is on, that means you plug in the key, that means maximum current is flowing. Once you put the key off, again current will become 0. That is how you change current in a circuit, or there are various other ways to change the current. You connect a rheostat and all, okay. So this is the primary coil where you are actually sending the current in this direction. So I will be giving the direction of cell current like this, okay. And for mutual induction, you should have one more coil where you just connect a galvanometer, okay. Initially there is no current flowing in it, but once you start sending current to this, you will see that the galvanometer will deflect. That means a current has been induced in this coil, and this coil is called secondary. Same theory will be applied when we do transformers also, okay. Now a current will be set up in the secondary, okay. What will be the direction of current? The direction of current should be such that it should be opposing, following Lenz's law, opposing the cause. Now here the cause of the current induced in the secondary coil is that the current is increasing. Once initially the switch was off, now I have put on the switch, okay. That means it does not want the current to increase, it will try to decrease the current. So induced current has to flow in opposite direction so that the value of this current will come down. So this will be the direction of induced current. This is called mutual induction, where the change in magnetic flux linked with one coil will be producing a current in the other coil, the neighboring coil of it, okay. Now like this one, if there is a change in current, there is a change in magnetic flux which is directly proportional to the current flowing, okay. If I just remove the sign of proportionality, I will just put a constant term. The constant term is called M, that is the mutual inductance, okay. It is not mutual induction, it is either called mutual inductance or it is called coefficient of mutual induction, okay. M into I. Okay, now like this one, you know EMF induced is equal to minus the rate of change of magnetic flux linked with the coil from Faraday's law, okay. Now E will be equal to minus d by dt of phi is nothing but M into I, or E is equal to M becomes a constant minus M di by dt. So this is the amount of EMF induced in the secondary coil because of the primary coil. E is equal to minus M, M is a constant, the rate of change of current, okay. Now if you take di by dt is equal to 1, like this one, E will be equal to minus M. So mutual inductance, the definition of two coils, is equal to the EMF induced in one coil when the rate of change of current through the other coil is unity. So you change the current here in such a way that in 1 second the current change is 1, okay, unity rate of change of current. The EMF induced here is equal to the mutual inductance of the secondary coil. And like in the previous case, in case of self-inductance also, SI unit of this mutual inductance is Henry, H-E-N-R-Y, named after a scientist, denoted by the letter H. Okay. Now if you want to define 1 Henry, it is the mutual inductance of two coils is said to be 1 Henry when a current change at the rate of 1 ampere per second in one coil induces an EMF of 1 volt in the other coil. So when is the mutual inductance 1 Henry? When the rate of change of current here is 1 ampere per second. Because of this, an EMF equal to 1 volt will be set up in the secondary coil. That time the mutual inductance of these two coils is equal to 1 Henry. Okay. Now Mutual inductance, the term M, depends on a few factors which is connected with both the coils. The factors which affect the mutual inductance are, number one, geometry of the two coils. Geometry here means what is the size of the coil, what is their shape, okay, what is the nature of material on which you wind the coil, okay. And the second factor is the mutual inductance of two coils also depends on the distance between two coils. If they are far apart, M will be less. If they are close to each other, M will be more, okay. And orientation of the two coils, how you place the two coils with respect to each other, that also will decide the value of M for the two coils, okay. Now we will come to a very important derivation. The derivation will be dealing with the mutual inductance of two long coaxial solenoids. Now you are familiar with the term solenoids. Now what is coaxial? Coaxial means the two solenoids having the same axis. I have got one solenoid, this chalk, okay, its axis passes from the center. On top of it, I will put a bigger solenoid, okay. The axis of the bigger solenoid also will be coinciding with the axis of the inner one. So here we will be taking two solenoids. One will be the inner solenoid and one will be the outer solenoid. Because these are two coils, they will be giving mutual induction on each other, okay. And you will be able to find out the value of mutual inductance of these two coils, okay. Let us consider two long coaxial solenoids, each of length L. So here I will take this one as the inner solenoid. This is the axis. Of course, you have to wind like this, current will be flowing, okay. Next, I will be taking the outer solenoid. I don't know if the chalk's color is visible, but this is the outer solenoid, same axis, wire is wound like this, okay. Current flowing here, I2, here it will be in the opposite direction, just opposite, it will be I2, okay, sorry, I1. And the length of each solenoid, they are of the same length. Long means the length is much longer if you compare it with the diameter of the solenoid, okay. I will name it as the inner one as S1, the radius of which is R1, and the outer one I will be naming it as S2, the radius of which is R2, okay. Now let a time varying current I2 flow through S2. Now we are taking the outer solenoid, okay, and we are studying the mutual inductance in the inner solenoid because of the outer solenoid, okay. Let a time varying current I2 flow through S2, which sets up a time varying magnetic flux, of course, phi 1 through S1. So because of the current flowing through the outer solenoid, a time varying magnetic flux will be set up in the inner solenoid. For the inner solenoid, phi 1, okay. So for S1 the flux is equal to phi 1, and you know that from the basics, phi 1 will be equal to M, that is mutual inductance of the first one because of the second coil, into, since it is because of the current in the second coil, it is M12 into I2. Let us take it as example, equation number 1. Okay. Now, the magnetic field due to current I2 in S2 is, now we are again coming to the outer solenoid, magnetic field B in the second coil, B2 is equal to mu naught N2 into I2. Now this N2 you need to be careful, it is number of turns per unit length. Okay, this is not the total number of turns, it is the number of turns per unit length of the solenoid. Because you know for a solenoid we have already derived B is equal to mu naught Ni. It was done in the previous classes. For a solenoid, the magnetic field induced in the solenoid will be uniform and it is equal to mu naught into N into I. Okay. Now, therefore, the magnetic flux through S1. Now, again coming back to the inner solenoid, we have deduced the magnetic flux. Okay. Now the magnetic flux through S1 is given by phi 1. Another expression for phi 1, one was this because of the inductance, okay. Second one, phi 1, which we already know, magnetic field into area into the total number of turns in S2, okay, in S1. Now phi 1 is equal to B2 is mu naught N2 I2 into area, because we are dealing with the first one, okay, A1, into what will be the total number of turns in the first coil, because we are talking about the magnetic flux induced here, S1, the total number of turns, N1 was the number of turns per unit length. So, the total number of turns will be in L length, N1 into L, okay. So, phi 1 will be equal to mu naught N2 I2, area cross section is pi R1 square into N1 into L. I hope it is clear so far, okay. Now I can write it simply as phi 1 is equal to mu naught N2 I2, N1 N2, just rearrange the terms properly, pi R1 square L into I2. Let us take it as equation number 2, okay. Now this was 1 and this is 2. Now we can compare or equate these two equations. We have phi 1 on the left hand side. So, I can write M12 I2 is equal to mu naught N1 N2 pi R1 square L I2, cancelling I2 on both the sides. I will get an expression for M12 is equal to mu naught N1 N2 pi R1 square into L. This is the value of mutual inductance on the first coil, that is the inner coil due to the outer coil, okay. Now if you have a material, some other material apart from vacuum, then this expression will be mu naught into mu r, just multiply with the relative permeability, okay. Now we can similarly find out the mutual inductance of S2 with respect to S1, okay, but here you should keep one thing in your mind that the magnetic flux due to S1, magnetic flux due to this S1 is confined solely inside, as if you go back to your previous classes, magnetic flux outside will be 0, okay. So, it is confined only within this one, okay. So, keeping all these into consideration, the solenoids are assumed to be very long, there is no magnetic field S1 due to the current in S1. Therefore, you will get the mutual inductance of the second coil, doing all the deduction as we have done previously. Again mu naught, if it is vacuum, mu naught N1 N2 pi R1 square into L. R1 because the magnetic flux due to S1 is confined in S1 only, so we are not taking this R2, okay. Now you see that equating these two, M12 is equal to M21. So, M12 is equal to M21, which is can be taken as M, whose expression is mu naught N1 N2 pi R1 square into L. So, this is the expression for mutual inductance of two coaxial solenoids, okay. Coaxial means they are having the same axis and they are we are taking the inner solenoid and the outer solenoid, okay. Again, if you replace the material inside these solenoids by any other material apart from vacuum, then this will come to mu naught into mu r and the expression remains the same, okay. That is all for today's class. We will proceed further in the next class. Thank you.